Chapter 9, Solving Quadratic Equations. 9.1 is Properties of Radicals. So here we have a radical expression, okay? And just a little vocab. Sometimes you'll see a little number up here in the corner, and that's going to be the index. So 3 is the index here, and that means that this is a cube root. It's where something raised to the third power is going to equal 8x, in other words, okay? And the part that's underneath the radical is called the radicand, okay? If you don't see a little number in the index like here, that means that it's a square root. Which means that you could write a little 2 in there because these are square roots. So square roots are the most common types of radicals. So we don't write the index for those, but the index is 2. Okay. All right. So that brings us to the product property of square roots. When you have two square roots multiplied together, you can combine them under the same radical, like so, right? And you can do the same thing with cube roots. You could actually do the same thing with fourth roots or fifth roots or sixth roots, but the index has to be the same when you combine the radicals, okay? So the index here is 3, and so you combine them under a cube root symbol like so, okay? All right, so let's see how this could be useful. So, you could put the square root of 2 into your calculator. It'll be a decimal, it'll be 1 point something. And the square root of 8 is not a perfect square either, so it'll also be a decimal. And you could put that in, but you can also use the this product property so that you can simplify this without a calculator, because these are both square roots. So I can say, okay, this is the square root of 2 times 8 then. And 2 times 8 is 16. Okay, and a square root means something times itself, something raised to the second power, is going to equal 16, and that would be 4. Right? So then no calculator needed there. Okay, and we can do the same kind of thing here. I can combine these under the same roof. So that's 12 times 3 under that square root. 12 times 3 is 36. And then 6 times 6 is 36, so the square root of 36 is 6. Okay? So you can do a similar kind of thing when you are dividing with radicals. So if you have a square root over another square root, you can combine them into the square root of that fraction, right? And a fraction is just division, right? And you can do the same kind of thing with cube roots. So let's try this out. So again, if you put these into your calculator, the different pieces, root 32 would be a decimal, so would root 8. And you could do that and then divide, but you can also say, oh, those are both square roots, so I can write it as just that fraction under a radical. And then 32 divided by 8 is 4. So now I have the square root of 4, which is 2. Okay. So let's try it again here. I can write this as the square root of 18 over 2. 18 divided by 2 is 9, and then the square root of 9 is 3. You can use this property with cube roots, and you can also use it in the opposite direction. So I can take this cube root, since there's a fraction inside the cube root, and I can break it into 2 pieces, like into 2 different cube roots, like so, okay? And then you could use a calculator to try to figure this out, but let's think about this. 3 times 3 times 3 is going to be 27, right? Because 9 times 3 is 27, so 3 to the third is 27. And with the cube root, I'm looking I need something multiplied by itself 3 times to get 27. That would be 3. There's nothing we can do with the top of that because we don't know what x equals. So I'd have to leave it like so. Okay. Okay. On the next page, we're going to look at simple radical form. Okay. So I'll get back to those instructions in just a second. Now the square root of 50, you could put that into a calculator again. The square root of 50 is going to be a little bit more than 7, because 7 times 7 is 49, right? So it should be 7 point something, and I can see it's about 7.1. Okay, but that's not an exact answer. This decimal would actually go on forever. It's just that's the maximum amount that my calculator will display. Okay, so this is not simple radical form if I say about 7.1. That's a decimal approximation. Simple radical form, what I want to do is the way I like to think about it is take the 50 and I'm going to break it apart into factors. So I'm going to think of a multiplication problem where the answer is 50. Okay, I don't want to use 1 times 50, but any other multiplication problem where the answer is 50. So 5 times 10, for example. Okay, or you could do 2 times 25. It doesn't matter. Okay, and then what I'm looking for is twins. So I don't have double 5s. I don't have double 10s. I just have a 5 and a 10. Okay. But I can keep breaking up the 10. I can't break up the 5 any further because it's a prime number. It just doesn't break up any further. There's no multiplication problem except 1 times 5 using integers where the answer is 5. But I can break up the 10 because that's 5 times 2. Okay? So here I've got it broken up all the way now. And I can see I do have twins. So anytime you have twins, if you think of this as a jail, the twins make a break from the jail, okay? One of the twins is going to get out, and the other one, sadly, gets shot by the guards and dies or something like that. Okay, so this is going to be 5 root 2. So those double 5s on the inside, because this is the square root of 25 is what this really is. Square root of 25 is 5. And then the 2, since it doesn't have a twin, is just stuck in the jail forever. And then that's simple radical form of the square root of 50, okay? So let's try another out here. So I'm thinking of a multiplication problem where the answer is 200. So how about 2 times 100? Okay, well, no twins yet. Can't break up the 2 any further, but I could break up the 100 into 10 times 10. Okay, now I found some twins. I could keep breaking up the 10s, and that's fine to do that. But I'm just going to, if they're grown-up twins, I just take them out because that makes my work easier, because this is the square root of 100, and the square root of 100 is just going to be 10, right? So a 10 is going to get out of the jail, and the other one doesn't, and then the 2 doesn't have a twin, just stuck in there, and there we go. Okay. Okay, so we can also do this with variables. So I'm going to start breaking up the 8. Well, 8 would be 2 times 4, so there still wouldn't be twins, but that would be 2 times 2 times 2 if I broke it up all the way, if I broke up the 8, right? And then x to the third means x times x times x. And y to the fourth would be 4 y's. Okay, and then I'm looking for twins, so let's see. I've got, well, there's 3 2's, but I'm only looking for twins when I have a square root. So I'm going to count that as a pair of twins, and that the third triplet's just left out of the jailbreak. Okay, and then for the x's, there's a pair of twins. That third x is going to be left out. And for the y's, I've got a pair of twins and another pair of twins. Okay, so everything that I circled, one of those is going to get out of the radical. Okay, so a 2 will get out, an x will get out, a y will get out, and another y will get out. And when you have multiple pieces that are on the outside, you're going to multiply them together. So that's why I wrote them like that. Okay, and then I look what's still left in the jail. There's a 2 in there and an x. And then I multiply everything all together. And then this will be in simple radical form. So this is going to be 2xy squared times the square root of 2x. Okay. Okay, so the other parts in simple radical form that I didn't talk about yet, we talked about the twins, and we're about to get to triplets for cube roots. If there's fractions, you want to reduce those, and we want to rationalize the denominators, and we'll get to that later too, but those are the other things to look out for. Okay, so next one. This is a cube root, so I'm not looking for twins anymore. I'm looking for triplets instead to get out of a third, and with a jail with an index of 3, you need triplets. Okay, so let's start breaking this apart. I'm thinking, okay, how about 6 times 9 is 54. No triplets yet. Let's keep breaking it up. I can break up the 6 into 2 times 3, and I can break up the 9 into 3 times 3. Okay, and then I see, oh, I do have triplets. So with the triplets, one of those triplets is going to get out, the others do not, because this represents 27, right? 3 times 3 times 3 is 27. Cube root of 27 would be 3. So I've got 3 times the cube root of 2. The 2 is just stuck in there, and there's simple radical form. Okay? All right, let's keep trying some more. I got cube root again, so I'm looking for triplets. So I'm thinking, okay, 4 times 4 is 16. Okay, I can still break up the 4s further into, each one of them breaks up into 2 times 2. Okay, and now it's broken up all the way. So triplets, let's see, there's 4 of those 2's, but I want 3 of them for the jailbreak. Same thing with the x's. So a 2 gets out from that first group, an x gets out from over here. And then I've got a 2 and an x still in there. So I could write this as 2x times the cube root of 2x. Okay, all right. Let's try another here. So, both these components are actually in simple radical form because you can only break the 10 up into 2 times 5. There's no twins there, and there's no twins here either. But if I combine them first, and I could write root 20. That's not incorrect, but I'm going to just break it up looking for twins anyway, so I might as well keep it like that. So 10 is 2 times 5. Okay? Now, I do have twins. It doesn't matter that the 2's aren't next to each other. They're still twins, right? So that still counts as a pair of twins. So a 2 gets out, the 5 is stuck in there, and I got 2 root 5. Okay? All right, next up. So this means 2 times the radical and then 3 times that second radical. So really I've just got a bunch of multiplication symbols. So what I could do is rewrite this. I could rearrange the pieces like that, right? So when I look at these, I just think I just multiply the parts on the outside together. You can do that, right? Because I could rearrange the pieces. So that 2 times 3 is 6. And then with the radicals, since they're both square roots, I can combine them under the same roof. So I've got 5. I'll just write it as 5 times x. And then this is going to be 5 times x times x times x, right? For the 5x to the third. Okay, and then I'm still looking for twins. I've got a pair of twins here. Let's see, this is going to be a little tricky to draw here. But I got a pair of twins there and another pair of twins there. So a 6 will get out, a 5 will get out, an x, and then another x. And in this case, there's nothing left in the radical. So then we don't need the radical anymore. You wouldn't leave an empty radical there because it doesn't mean anything, okay? And so this would be 30x squared when we multiply it all together, okay? All right, so I'm going to take the number pieces. Well, there's no number in front there, so this would just be a 3. And then I'd have 4x times 8x to the third. I'm just kind of breaking that apart a little bit. And I can still break up the 4 and the 8, right? So let's go ahead and do that. 2 times 2 is 4. And then 2 times 2 times 2, if you broke it up all the way, would be 8. Okay, and then I'm looking for triplets here. So hey, I've got triple 2's here. I've got triple x's here. And then those are my leftovers, right? So let's see. There's already the 3 on the outside. Now there's going to be a 2 that joins it and an x. Okay, and then I multiply everything back together. So this would be 6x on the outside. And then I've got the cube root of 4x. Okay, and that is in simple radical form. You could actually, just looking at this one, you could simplify just that second radical because you'd have 2 times 2 times 2, x times x times x. And then, you know, these end up being the leftovers over here. So that would work too on that one. Okay, so next up, let's look at rationalizing the denominator. All right, so this says write this in simple radical form. So at first glance, hey, there's no twins down there in the radical. So that's good to go in that respect. We can't reduce the fraction because 3/7 doesn't reduce. Plus, this is in a radical and that's not. But there's another problem, and that's that there's a radical in the denominator. So that means there's a square root or a cube root or something like that in the bottom of the fraction. And that's against the rules for simple radical form, okay? So here's how we can handle this. Since there's no, we got to get that 7 out of the radical. And since there's no twin for the 7, what we're going to do is clone a twin, okay? So what I'm going to do is I'm going to multiply the bottom by the square root of 7. Now I can do that as long as I do the same thing to the numerator. Because if you think about it, then we're just multiplying this fraction by 1, right? Anything over itself equals 1. So we're not changing the value of this fraction. We're just changing its form. We're kind of unreducing it in a way, if you want to think about it like that, okay? And then I'll multiply straight across. So on the top, that's going to be 3 times the square root of 7, just 3 root 7. On the bottom, I have root 7 times root 7. Well, I could combine them under the same roof. And now I have twins, right? That would be the square root of 49, which is going to be 7, or you can think about the twins. And then I've got 3 root 7 over 7, okay? You do also want to check to see if you can reduce fractions. Some people would reduce the 7s, but you can't do that because the one's in a radical and one is not. But I would want to check the 3/7 part, and that part already is reduced, right? You can't reduce that, so that means this one is good to go, and that's in simple radical form, okay? So let's try another here. First thing I would check, is there twins? It's just 2 times 3 if you break it up all the way, so no twins. So then let's clone a twin for the 6, like that, okay? I'll multiply straight across. Okay, and now I do have twins, so this is going to be 2 root 6 over 6, okay? Now this one, I can go a little further. Can't reduce the 6's because one's in a radical, one isn't, but you can reduce the 2/6 part. 2/6, well, 2 goes into both of those, so that would reduce to 1/3. So I'm going to write my answer like you could put the 1 in front of the radical, but you don't need it, right? So this is going to be root 6 over 3, okay? All right, now I've got a cube root, and it's tricky here. So I see a lot of people, a lot of students will do this. And I totally understand why, because that's pretty similar to what we did on the previous problems. But this time, since it's a cube root, we need triplets, okay? So if you multiplied on the bottom, you'd have the cube root of 5 times 5. You still wouldn't have any triplets, okay? So what you'd want to do here, I'm thinking I've got 1 5. That means I need to clone 2 more 5s to get a total of 3 5s, so I have triplets. So I want to do this. Now I've got 2 5s in there, right? And whatever I do to the bottom, I have to do to the top as well. So that's supposed to say 5 to the second there. Got a little messy, okay? So on the top, I've got 2 times the cube root of 5 squared. And 5 squared, I just have 5 times 5. I can't break it up any further. So there's no triplets there, but that's okay because it's in the numerator. It's okay to have a radical in the numerator, okay? And on the bottom now, I would have 5 times 5 squared. Well, there's 5 times 5 squared. Now I have triplets, right? And so then this would be 2 times the cube root of 25 all over 5. Okay, and I'd also want to check the 2/5 part, and you can't reduce that, so that one is finished. Okay. So on this one, you could multiply by the cube root of 9 squared to get the triple 9s, and that's fine. But you can take a little shortcut here, just because I could write it like that, right? And I've already got 2 3s. That means I only need 1 more 3. Okay? So this is what I'm going to do to the top and bottom so that I get the triple 3s down there. If you multiply by the cube root of 9 squared, it will work out. You'll just have to do some reducing at the end. Okay? So I've got the cube root of 3 then over the cube root of 3 to the third. And then the cube root of 3 to the third is going to be 3. So now I've got the cube root of 3 all over 3. Okay? All right. Next up, let's look at conjugate pairs. So here's a conjugate pair. A plus the square root of b and a minus the square root of b are a conjugate pair. Okay? So if I'm looking for the conjugate of 4 minus root 7, all I have to do is change the sign of the radical. Okay? So the conjugate of 4 minus root 7 would just be 4 plus the square root of 7. Okay? You just change the sign of the radical part. Okay? Just a little vocab. We're going to need that on the next page. All right, last set of problems. There's a lot in this section. Okay, rationalizing denominators in the form a plus or minus square root of b. That's supposed to be plus or minus there. Okay, so on a problem like this, there's a radical in the denominator, and that's not in simple radical form then. Okay, so what some people will do is say, okay, that's a square root. I need another 3 there, so I'll clone a 3 like this and do the same thing to the top. But if you do that, that would work on this part, but you'd have to multiply the whole denominator by the square root of 3, which means you'd have to distribute, and then you'd still have a 2 root 3 over there. Okay, so that is going to be the wrong way to go. Okay, that's a dead end. What you want to do when you've got something plus or minus a square root is multiply by the conjugate of the denominator. Okay, so the conjugate of 2 plus root 3 would be 2 minus the square root of 3. Okay, and then whatever I do to the bottom, I got to do the top as well, so that I'm really just multiplying this fraction by 1. Okay, and then I'm going to multiply. So on top, I'm going to distribute the 1, which doesn't really do much. That gives me 2 minus the square root of 3. Okay, but on the bottom, I've got now 2 plus root 3 times 2 minus root 3. And to simplify that, I'm going to have to FOIL. I've got a binomial times another binomial. Okay, so I'm just going to write FOIL here. So we're still just working on the denominator. Okay, so the first, I'm going to do 2 times 2 would be 4. Outer, I've got 2 times negative root 3. So 2 times negative root 3, a positive times a negative, that would be negative 2 root 3. On the inside, I've got root 3 times 2. Well, we'd write that as positive 2 root 3. Okay, and last, I'm looking at the pieces at the end. I've got positive root 3 times negative root 3. Okay, so positive times a negative is going to be negative. And then I can combine the 3's under the same roof. Okay, like so. Now, it seems like we still got lots of radicals in the denominator, but hang on. If you look in the middle, I've got positive 2 root 3 and negative 2 root 3, and those just cancel each other out. That's pretty nice. And I've still got a radical here, but it's a square root, and I have twins, right? So now I've got 2 minus root 3 on top still, and I've got 4 minus, and then, because it's minus this, people forget about the minus for some reason there, and then the square root of 9 would be 3, right? So now I can say this is 2 minus root 3 all over 1. And when you're dividing something by 1, that doesn't change its value, so I can just write this as 2 minus root 3 then. And that's simplified, and that's in simple radical form now. Okay? All right, let's try another one out. Get another pen. My pen's dying there. Okay, so this one I'm going to multiply by the conjugate of the denominator. Okay, and I got to do the same thing to the top. All right, so that means on this one I'm going to distribute to simplify the numerator. Okay, I just thought 2 times 3 is 6. 2 times root 5 is 2 root 5. On the bottom, I'm going to be FOILing. Okay, so the top's going to stay the same. The numerator is the same. Let's FOIL now. 3 times 3 is 9. The outer, 3 times root 5 is 3 root 5. Inner, negative root 5 times 3 is negative 3 root 5. And last, I've got negative root 5 times positive root 5. Well, a negative times a positive would be negative. And then I've got, I can combine those 5's under the same roof. Okay? And once again, the outer and inner down here, the two middle parts are opposites. That's going to always happen when you multiply conjugates together. So you really don't need to do all of FOIL when you're multiplying conjugates. You just need to do the first and the last. Okay? And I can simplify this part too. So I've got 6 plus 2 root 5 all over 9 minus, and then this would be 5. Okay, got it down to this. There's actually another step though, because we can still reduce this fraction, okay? So what you want to do is look at all three terms. So when you're looking at all three of these terms, I'm thinking, does anything go into all three of these? And they're all even numbers, right? So that means I could divide them all by 2. So that's what I want to do to reduce this. But you can't just reduce like those parts and not reduce the part with the radical. You gotta reduce all three parts at once. So this is going to be then 3 plus the square root of 5 all over 2. So I took half of all of those terms, right? It's supposed to be a 2 down there. Okay, that's the end of the section, and I'll see you next time.